Okay, welcome to the last part of this lecture. We have been looking at RDF definition, the motivation, and the syntax of RDF, And in this last part, we will be looking at the RDF schema. Now, recall the difference between RDF and RDF schema. So we call it RDF schema or RDFS. And as you recall from the last video, we said RDF allows you to model knowledge, so to represent certain things with using a specific syntax. And now we will be looking at RDF schema as a way to express semantics. So this means that once we have model knowledge, we can also start inferring certain things. The main technique we use to infer knowledge based on the on what we represent is using a reasoner, which will do the inferences for us. We will look into this a bit later with the ontology engineering classes. But for now, you need to remember that the difference is between syntax and semantics, so modeling versus inferring knowledge. And today we will be mostly looking at how to allow this inference. Just a small parenthesis, what we mean by semantics. If you're familiar with, this is an example from programming languages. If you're familiar with programming, most of the time you have a certain when you write a function, you have a certain syntax that you use. It could be Python, it could be Java, it could be a Prolog. And so you use specific symbols for that are allowed by the language. And then this syntax has different types of semantics. So, for example, the intended semantics is what the program means. In this example, we mean this syntax allows to compute factorial numbers. We have a formal semantics. So the formal semantics is a way to formally write the functions. What is the mathematics behind this program? And finally, you have procedural semantics. So what actually happens when what the program does, what actually happens when the program is being executed. So in the same way, we need to think of different type of semantics. So what is the formal semantics RDF that we express with RDF schema, and what is the intended semantics that the symbols that we use allow us to express, and also what happens once we run the reasoner following certain symbols. If you think of RDFS, you need to think of a set of special keywords. This set of special keywords is nothing but a vocabulary. So we will see different type of vocabularies over the course, and RDFS is the one you need to get more familiar with. This vocabulary allows you to specify a number of things. So when you represent your knowledge graph and you start creating your triples, there are things you want to express, and there are things that if you express, you will be able to infer as well. We can, for example, specify that something is a class. For example, a teacher is of type RDFS class. So this is a special keyword that says anything that is of type class will be considered a class. Or we can start creating taxonomies. So a teacher is a subclass of a person, maybe an examiner is a subclass of a teacher. So we can start putting classes into a relationship together to create a taxonomy. So subclass of is a predicate in the RDFS vocabulary that allows you to create taxonomy. The same way we specify the things are classes or subclasses, we can also specify the things are properties. So teaches course is a predicate that is of type RDFS property. This is the special keyword in RDFS. Or that something is a sub-property. So for example, teaching a module means teaching a course, but it's a sub-properties of the properties that we previously expressed. This you will see often RDF type, RDFS class, less often RDFS property. This is not being used, and sometimes subproperty of. The one you will see very often is probably subclass of. The other most important thing you can specify when with RDF schema is that something is an instance of a class. So Ilaria, for example, is RDF type teacher. You need to think of classes in within RDFS as buckets or where you can fit element into. So you have the concept teacher. So a class is a concept in certain sense. You have the concept teacher, and then you have multiple teachers at the foo. So this can be Ilaria, it can be Romana, it can be anybody else. The same way when you specify that a class is of type class, an RDFS class is actually a concept which encompasses all the classes existing in your knowledge graph. We will see this this later on. The other special keywords that you will be seeing very often is keywords that allow you to constrain properties with certain classes. This means, for example, that if we create the property teaches course, we want to make sure that this property always relates to teachers and to courses, and not, for example, to students. Therefore, we use RDFS domain and RDFS range to express the classes we want to appear in subject or object positions. This means that every time we will use teaches course, the subject will be an instance of the class teacher, and the object will be an instance of the class course. So these domain and range concepts are really important because it's these are keywords that allow you to restrain the domain of your property, which means that your reasoner will be more effective if you use them. These keywords are combined with the keywords we saw earlier. This means that there is if you use them in combination with sub-properties or the concepts can be inherited. This means that if you say teaches module is a sub-properties of teaches course, you can also infer that the teaches module can only be appearing with a subject of type teacher and can only be appearing with a subject of type course. So sub-properties inherit from the property that is sub-property of. Now with RDF schema, you can specify other things. You can give something a name. For example, Amsterdam has a label Amsterdam in Dutch. Recall that we said these are the values that are quoted are literals and not URIs, while these two subject and predicate are URIs. We use RDF schema to comment on something. For example, Amsterdam has a comment. It's a fantastic city, and then we can also use RDF schema to refer to similar resources. For example, RDFS also. So we might have Amsterdam in a certain knowledge graph. This is the Wikipedia, which is a famous knowledge graph. and it is linked to another knowledge graph, which is Wikidata, and you can express things like, okay, if you are interested in Amsterdam from Wikipedia, you might also want to be able to see the information you can find in Wikidata. So these three keywords are quite common, especially the RDFS label, because sometimes the URIs are not that meaningful to the human eyes. So I could replace Amsterdam with any kind of symbol and still the label would be Amsterdam. So the RDFS label is the property that allows human to understand what the resource on the web is actually about. When we represent an RDF schema, we use these symbols. We can use these symbols to allow inference. So we could say, for example, that we have Netherlands, which is of type European country. So if we define RDF type, this means that this is a class and this is an instance. And this class, European country, is a subclass of another class. So subclass of can only be used between classes. You can never use subclass of between an instance and a class, or between an instance and an instance. So we specify European country as a subclass of a country, and then we specify the properties that relate to these classes. So, for example, we say that these the properties are highlighted in blue to remind you that when we represent properties in a schema, so using RDF schema, properties are also considered classes. So these can be quite confusing, but it's only a way to represent this information in a graph format. So what you are actually seeing here is that the property contains cities, has a certain range, which is city, has a certain domain, which is country. This means that contained city is a property that can only appear with a subject of type country and with a subject of type city, with an object of type city. Similarly, we can define a subproperty as capital, and which can only appear with objects of type capital. Notice that when we then express information about instances of this class, we use the has capital property as a proper edge in the graph. So in the end, we get the Netherlands has capital Amsterdam. And what all these symbols, these highlighted symbols, which we call reserved symbols, they allow to do inference. This means that I can materialize certain relationships just because I use these special symbols. The materialized statements are the ones that that you see in dashed lines here. We make when we use RDFS, we make a difference between asserted triples and inferred triples. The asserted triples are the ones that were expressed originally in your knowledge graph, and the inferred triples are the ones that the reasoner generates or materializes based on the keywords or the reserved symbols that you used in RDF schema. So somehow you see that you can basically create, you can create a smaller graph with less asserted triples, and then use a number of reserved symbols to generate more knowledge. So here we have almost double the knowledge, for example. So if we go into, if we look into the examples of triples that have been inferred, So we see, for example, that Netherlands was type European country, but we also know that a European country is a subclass of a country. By specifying these two relationships, we can infer that Netherlands is also of type country, because the subclass of relationship is transitive. This means that you can infer the type of an instance by following the taxonomy that of its class. So its class and the superclasses of this instance. We can, since in the same way, since a European country is a subclass of country and country is declared as of type RDFS class, we can also infer that European country is of type class. So this is another example of a transitivity. So subclass of allows you to infer transitive relationships. The same happens with properties. So actually here the property contains city and its subproperty are inferred to be an RDFS property, only because they have expressed RDFS range and domain. So you can only express range and domain on properties, never on classes. This means that by defining contained cities and has capital as properties that have a range and a domain, then you can automatically infer that these are instances of a property. Now let's look at another one. Here we have another example. Netherlands has capital Amsterdam. We have this relationship, and what we can also infer that if the Netherlands has capital Amsterdam, the Netherlands also contains a specific city, which is Amsterdam. This happens because we know that as capital is a subproperty of contained cities. So since we have declared that this is a subproperty and this relationship holds between the two, therefore this relationship will also hold. Then we have so Amsterdam is inferred as being a capital, and is inferred as being a city because we expressed this the domain and range of these properties. So we say that the has capital is always appearing with instances of a capital class, and therefore Amsterdam will be an instance of a capital. And the same, since this is being inferred, since Amsterdam is a city that is the object of the contained city, is the range of the contained city relationship, therefore it will also be inferred as being of type city. So this will become this is very useful to understand what does it mean, what are the inferences that a reasoner does. I recommend you to look at these slides a bit more in depth to understand and try to explain yourself all the why certain triples are being materialized, are being generated. And if something is not clear, we can always discuss this in class. Now, one thing to remember is that the reasoning engine, so the inference does not depend on the syntax that you have in your knowledge graph. So we said that the URIs can express concepts on the web, but we can use any kind of symbols, and any kind of symbol also means symbols that we humans don't necessarily understand. What is really important is not the symbols that we use to represent the URIs, but the special keywords that we use. So this will allow the reasoner to still generate this, exactly the same triples independently of what you have inside, what you have used as symbols. This means that what expresses the semantics is actually the special keywords and not the RDF symbols that you used in your original file. And one last note, when we look at this this graph, we often, when we represent knowledge graphs, we often distinguish between two different levels. One is the ontology level, which represents all the information about the classes, the properties, the domain and ranges, sub-properties of, subclass of. This is the ontology level. We also call it the schema level or the T-box, terminology box. Anything that represents instances of the classes and the actual relationships between classes is called the data level, the assertion box, so the box where we assert facts, or the instance level. So you always need to remember this distinction, especially because domain and range and properties as classes appear in the T box, never in the A box. So with that, we just remember a couple of conventions when you write RDF and RDFS file. Try to use underscores to represent instances. For example, Frankie D. Young. If you don't use spaces, white spaces, but because we're using URIs, white spaces would be misunderstood. So use underscores for the instances, and then use the upper camel case syntax to represent classes, while you use the lower camel case syntax to represent properties. So this will allow you to, very often, if you follow this syntax, you will be able to easily read a new RDF file and understand, okay, this is a class, this is an instance, this is a property. With that, we finished the class on RDF and RDF, the first class on RDF and RDFS. Thank you very much, and see you in the next class.